Download this code from codegive.com, link in the description below. OK, let's dive into Koichi Sasada's Rubyconf 2016 talk on Ruby 3 concurrency, which was a seminal presentation laying the groundwork for what eventually became ractors in Ruby 3. While the specific implementation changed somewhat between that talk and the final release, the core concepts and motivations remain relevant. This tutorial will break down the key ideas, challenges, and approaches discussed, and provide illustrative, though potentially slightly adapted, code examples to reflect the evolution. Title: Ruby 3, Concurrency. Presenter Koichi Sasada, MRI Ruby Committer. Rubyconf 2016. The need for concurrency in Ruby. Sasada's talk started by highlighting the increasing importance of concurrency in modern software development. Here's why. Hardware evolution. Multi-core processors are ubiquitous. To fully leverage these processors, programs need to be able to execute tasks in parallel. IO-bound tasks. Many applications spend a significant amount of time waiting for I/O operations, example network requests, database queries, file reads. Concurrency allows other tasks to run while waiting, improving overall throughput. Responsiveness. In interactive applications, like web servers, concurrency helps ensure that the user interface remains responsive even when computationally intensive tasks are running in the background. 2. Challenges with existing Ruby concurrency models. Before Ruby 3, Ruby's concurrency options had significant limitations. Global Interpreter Lock, GIL. The GIL allows only one Ruby thread to execute at a time within a single Ruby process. This severely limits the ability to use multiple cores for CPU-bound tasks. Threads are useful for I/O-bound work. MRI's threads. MRI, MATS's Ruby interpreter, provides threads, but they are green threads managed by the interpreter, not native operating system threads. While they provide concurrency for I/O-bound operations, the GIL prevents true parallelism. Processes. Using multiple processes, example with fork or libraries like Parallel, can bypass the GIL, but processes have higher memory overhead and complex inter-process communication. Data needs to be serialized and deserialized, adding performance overhead and complexity. Event machine / async. Event machine and other asynchronous libraries provide concurrency through an event loop. They work well for I/O-bound tasks, but can be complex to manage state and debug. They also often require significant code restructuring. Fiber. Fibers provide lightweight concurrency, allowing switching between different execution contexts. However, they still operate within the same thread and are not inherently parallel. 3. Sasada's vision for Ruby 3 concurrency. Sasada's primary goal was to introduce a concurrency model that could 1. Achieve true parallelism, utilize multiple cores. 2. Minimize memory overhead compared to processes. 3. Be easier to use than existing options. 4. Maintain Ruby's existing thread semantics as much as possible. 4. The key idea: isolation and memory sharing. The core concept was to create isolated contexts or units of concurrency that could execute independently and in parallel, while also allowing controlled sharing of data between them. This balances the need for parallelism with the need to share data efficiently. Key aspects of the isolation/sharing model. Isolated memory spaces. Each concurrent unit has its own separate memory space, reducing the risk of race conditions and data corruption. Message passing. Communication between concurrent units happens primarily through message passing. This ensures that data is copied rather than shared directly, preventing concurrent modifications. Controlled sharing mechanisms are provided to allow certain objects to be shared safely between concurrent units, especially for read-only data or immutable data structures. This avoids unnecessary copying. Introducing ractors, the evolution of sasada's ideas. While the specifics presented in Rubyconf 2016 were slightly different, the evolved form of these ideas manifested in Ruby 3 as ractors. Ractors are isolated execution contexts. Ractors are independent. Each ractor has its own thread and memory space, allowing true parallelism. Message passing for communication. Ractors communicate by sending messages, objects, to each other. When a ractor sends a message, the object is copied to the receiving ractor's memory space. This prevents data races. Shareable objects. Certain objects can be shared directly between ractors without copying. These include immutable objects, like symbols, numbers, true/false/nil, and objects that are explicitly marked as shareable. 6. Code examples, ractors in action. Let's illustrate ractors with some code examples. Explanation *. 1 ractor.new do, and, creates a new ractor. The code inside the do, and block is the ractor's code. 2 receive, pauses the ractor's execution until it receives a message from another ractor. 3 ractor.yield, sends a message back to the ractor that sent the initial message. It also marks the ractor as ready to receive another message. 4 r.send, sends a message to the ractor r. 5 r.take, receives a message from the ractor r and removes the message from ractor's mailbox. Explanation *. 1 ractors equals, 1 number_ractors, .map ractor.new. Creates an array of number_ractors. Each ractor is initialized with code that waits for messages, performs long_calculation on the received value, and then waits for another message. 2 ractors index %number_ractors.send, n, sends the data n to a ractor to be processed. The modulo operator, %, distributes the work evenly among the ractors. 3 ractors.each, and close, after sending all messages, it sends a close message to all ractors. Close indicates that no more messages will be sent. 4 ractors.each, and take, consumes each ractor thread. Important notes *. Shareable objects. Objects that are mutable must not be shared between ractors without proper synchronization or protection. Use message passing to exchange data safely. Consider using immutable data structures. If an object needs to be shared, look into ractor.make_shareable. Error handling. Ractor exceptions are not automatically propagated to the main ractor. You need to explicitly handle them, example by sending error messages back. Deadlocks. As with any concurrent system, be careful to avoid deadlocks when ractors are waiting for each other. Ractor.yield versus ractor.send plus ractor.take. Ractor.yield only sends to the ractor that initiated communication using send and take. Other methods of sending messages don't have the yield feature. 7. Shareable objects, deeper dive. Ruby 3 offers ractor.make_shareable, object, to mark an object as safe to share between ractors. However, use this with caution. Immutable objects are safe. Numbers, symbols, true, false, and nil are inherently shareable. Explicitly marking as shareable. You can use ractor.make_shareable, object, to explicitly mark an object as shareable. The object and all its contained objects must be immutable, frozen, or thread safe for this to be safe. Ruby will attempt to verify this, but it's your responsibility to ensure data consistency. Data structures and thread safety. Use thread-safe data structures like concurrent array and concurrent hash from the concurrent Ruby gem if you need to share mutable data structures. Even then, be very careful. Frozen objects. Freezing an object.freeze, makes it immutable, but only if all the object's members and their members are also immutable and frozen. 8. Actor model versus ractors. It's important to note that ractors are not a full implementation of the actor model. The actor model typically includes features such as mailboxes. Each actor has an independent mailbox to queue messages. Ractors have mailboxes. Behavior. An actor's behavior can change based on the messages it receives. Creation and supervision. Actors can create child actors and supervise their behavior. Ractors provide the fundamental building blocks for concurrency, but you may need to implement some of the higher-level actor model concepts yourself using ractor primitives. 9. Conclusion and further exploration. Koichi Sasada's RubyConf 2016 talk provided a compelling vision for concurrency in Ruby. Ractors, the result of this vision, offer a powerful tool for achieving parallelism in Ruby 3 and beyond. To deepen your understanding, I encourage you to experiment with ractors. Write your own concurrent programs and explore the capabilities and limitations. Read the official Ruby documentation. The Ruby documentation provides detailed information on ractors and their API. Explore libraries. Investigate libraries like Concurrent Ruby that provide thread-safe data structures and other concurrency primitives. Study the actor model. Learn more about the actor model and how it can be applied to design concurrent systems. Monitor performance. When using ractors, carefully monitor your application's performance to ensure that you are actually achieving parallelism and not introducing bottlenecks. Concurrency is a complex topic, but ractors provide a significant step forward for Ruby developers who need to leverage the power of multi-core processors. Remember to design your concurrent applications carefully, paying close attention to data sharing, synchronization, and error handling. Good luck.